All right, in this lecture, we're going to digress to a new topic. Well, it's not a digression, it's an important topic. It's just not in the same line as the scattering theory we've been working on and the fundamentals of wave packets and time-dependent Schrodinger equation, but we'll get back to that. I'm trying to catch the essence of some of the most important prerequisites to QED, and field equations are certainly in there. Now, there is an argument to be made that the study of field equations belongs to the study of quantum field theory, right? You take your quantum field theory course, and step one, you study the field equations. And you study the classical field equations, the field equations of relativistic quantum mechanics, RQM, right? Relativistic quantum mechanics, that would be the ones we're going to talk about today, the Klein-Gordon Equation, and then later the Dirac Equation. But we don't study the quantum field theory. We study instead relativistic quantum mechanics. And that would be taking the Klein-Gordon Equation and the Dirac Equation and maybe even the Proca equation and just solving them like you do the Schrodinger equation. We're probably not going to spend a lot of time doing that, but we are going to introduce these field equations because that is prerequisite to studying the quantum versions of the field equations, right? Where you put a Q here, where you quantize the field. So in order to quantize the field, you have to kind of understand the field, right? And the thing that's going to be quantized. And that's often done in the beginning of a quantum field theory course. So it's arguable that this is not a prerequisite. However, if you have a really good quantum mechanics course, you actually do touch on the subject of relativistic quantum mechanics, and you do study these field equations. And there's also classical field theory too, which talks about these field equations. So that's why we're going to consider it a prerequisite, and we are going to discuss it here. So we will begin with the Klein-Gordon equation, and then we will do the Dirac equation. And this will just be an introduction to these ideas. In other words, we'll talk about the equations, but we're not going to solve them for any particular circumstance. Well, we'll probably solve them for the free particle, right? We'll solve them for the free particle, which is what we do in elementary quantum field theory, right? It's solved for the free case. And we'll call that good, and that will be the foundation for what we're going to work on. Okay, so, also this is very good because it binds together a bunch of different things we've already learned. For example, we've learned about the Lagrangian formulation, the Lagrangian formulation of quantum mechanics, of classical mechanics for that matter. And we've learned about Nether's theorem and the conservation laws and the currents. And we're going to discuss, so we've already talked about those things in the context of special theory of relativity. So now we're going to apply them to these field equations. So there's a lot of richness here, and it's definitely worth taking some time to study. It's a lot of notational richness too. So we're going to cover a lot of the different notations. And also, I'm going to reference Wikipedia's article because that's kind of where people land, right? So, for example, here's an excerpt right from Wikipedia about the Klein-Gordon equation, right? And here's its story about the solutions, right? This is as good as any textbook. It's just so brief, and it's not full of a lot of commentary. But there's no reason to rewrite the wheel, right? Or to reinvent the wheel, because this is just fine reference material. It's available to anybody in the world. And there's no reason we shouldn't use it as some kind of foundation for our work instead of recreating it all. However, in some sense, I will actually recreate it all anyway. But we will get back to this because it really does a beautiful job of going through some of the different notations. That's really important, and that's what's done here. We'll talk about that too. Okay, so enough introduction. Let's begin. All right, let's begin by looking at some of the conventions that we're going to use here. I've actually got a pretty big mind map of this whole thing. I'm trying to build a mind map of all of this stuff. I think that's a pretty good way of doing it, of organizing thoughts. But let's begin this mind map with our conventions. And these conventions I've written down right here. And let's go through them because they will pervade our study of the subject, and you really need to see these conventions so you can check when you look at other textbooks, how do they use different conventions? Although I got to say, most textbooks use the ones I have gathered here. So these are a very good, safe bunch of conventions to know. But we start with what we call the mostly minus convention of the metric. Now, the metric is written in some textbooks as G mu nu, and as other textbooks as eta mu nu. Now, I prefer eta mu nu. I'm erasing that function of x because the reason I prefer eta is whenever I see G, I always think of the metric tensor, which is a function on the space-time manifold that you're working. Now, we're working in just regular flat space, right? So every point in our space is located in four-dimensional space, right? With x1, x2, x3 is the spatial axes, and then this sort of time thing that goes on out there that we can't draw in there because we can't draw four dimensions. But if you were thinking in terms of the manifold of space-time, this is the simplest possible thing you can have, right? It's just flat space. It's got one so-called chart, and the mapping is basically the identity mapping, right? So it's very, very easy when you're dealing with special relativity. Basically, we're using the space-time of special relativity here. So there's no gravity. And whenever I see G, I think gravity. And that probably is because I'm really familiar with general relativity, and we use G all the time, and G is a function of space-time. And in general relativity, whenever we use eta, we basically mean flat space. And the difference is that eta is a constant. Every point in space, right, no matter where you are, you've got this mostly minus metric. Now, I've also written this convention in a way that anybody who's familiar with this channel and the way we discuss this, it's really very, very sketchy in the sense that this object as written with mu nu is not really a metric. Right? I mean, not really a matrix. This is a matrix. I've drawn it as a matrix, the 0, 0 element, the 1, 1 element, the 3, 3 element, right? And we all know by now, or you should know, that an object with two down indices is really not expressible as a matrix. However, it is so uniformly done in field theory textbooks that we write it this way. Now, to be fair, very rarely do they actually use it as a matrix. They just present it in order to capture the value of every possible combination of mu and nu, so you can look it up very quickly. So it's a fast way of presenting all these values. Another way you might sometimes see it is equals diag 1 minus 1 minus 1 minus 1. But that's not any better because when you write it this way, you're still it's the diagonal of something, so it's clearly the diagonal of a matrix. So that doesn't solve the problem, really. Anyway, the real solution is just to list them off. Eta 0, 0 equals 1. Eta 1, 1 equals minus 1. Eta 0, 2 equals 0, right? That's the real way to do it. Anyway, the preference is to use this symbol for me, but you will see in a lot of field textbooks, they still use G, but they assume that G is not a function of space. Well, it's a constant function on space-time, and the components have these values. Okay, so enough about that convention. Once you have this convention in place, then you start talking about how do we write down the components of our four vectors and the contravariant components of the four vector P. And I've chosen P because it's momentum, but it could be any four vector. It's the P0 component, which is a scalar component, and then it's got this vector part, which represents, basically, this is the same as P0, P1, P2, P3, right? This is a shorthand way of writing this. This is and this are the same. This is shorthand. Now, in textbooks, this will be boldface, right? But I don't really have access to boldface on this whiteboard, so I'm going to use this little vector symbol on top when I need to. But it's shorthand. Understand it's shorthand, but it's a very valuable shorthand. And we're going to see how in the standard book of my generation of learning this, which is a book called Peskin and Schroeder, which I'll put a reference in the show notes to, because it is a critical book for me to use, and it's where most of this lecture was generated from. Definitely exploits this notation to its fullest. Now, the covariant components of a 4-vector are the same. You use this to lower them, right? You have the eta mu nu to lower the components. And when you lower the components, these 3 minus signs come in and they just lower the sign of P. And then other parts of the notation that are important is when I write P dot X, when I just write P or X or any 4-vector, this is the whole 4-vector, right? This, if you just write the letter down, like for example X, this is going to be X0, X1, X2, and X3. Although X and P will be likewise, P0, P1, P2, P3. So if I write down P, I'm actually writing down basically this. In fact, this is a little awkward, right? Because here I've written down P mu with an upper index, but I'm referring to the whole vector, right? If you substituted P0, then what would you do? You'd have to get rid of this piece. But this is sort of how it's written in field theory books, right? It's got the understanding that if I write P0, I'm only referring to this piece. If I write P2, I'm referring to the second component of that piece. And you will find this literal notation inside Peskin and Schroeder, and it is a bit awkward. You would probably prefer to write it just like, you would probably be better to write P equals this. The problem is that, what do I write for this then? How do I indicate the covariant version of the 4-vector? And the answer is, well, you just sort of take this hit and you abuse the notation. This is sometimes called an abusive notation. And you write it down this way. You say P contravariant, the components look like that, and P covariant, the components look like this. And these are numbers, right? So whatever the number P up 0 or P, whatever the contravariant 0th component is of P, you know that the covariant 0 component is the same, right? That's how these are linked. It's really means to be the same. And here it's telling you that these change sign, right? So if you assign these values, then you immediately know these values. And the reason is because you know the metric. So this notation is a little bit abusive in some sense, because this is just a single number, and here I have some kind of parenthetical with, this is a quadruplet of numbers. So how can a single number be equal to a quadruplet? And the idea is, well, no, I pick the member of the quadruplet that's equal to this number is what the implication is. Okay, enough about that. Let's move on. All right, the next convention is the dot product. So when I take two 4-vectors, P and X, notice this is the full 4-vector. I'm going to take a vector product, a dot product between the two. And what this literally means is, these are all equivalent, right? That's the whole point of this convention. What do we mean by the dot product of two 4-vectors? Well, we mean you can take the contravariant components, and with this aid of the metric, you can create, you can contract on a contravariant and covariant index, and you end up with this expression here, P0, X0 minus vector P dot vector X. And here you see we're starting to exploit this shorthand that I was talking about earlier, right? This shorthand where we deal with these vectors, right, comes together where now we can use the regular dot product of 3 space that we're so used to from regular physics. And that's one of the advantages, is all these notations are trying to make things feel like you've done it before. And it's really kind of almost gimmicky in a sense, because struggling to get it to look like what you're comfortable with almost obscures things. But I think in this case it's all very efficient and it works very nicely. The point is that the dot product of two 4 vectors, in the end, it just has this weird Minkowski-esque form that is so famous in special relativity, and you can't get away from it. So this is the convention. The only exception I would have to this is I would prefer this to be eta here, right here instead of g, but whatever. That's a small thing. But with that convention, we talk about the square of any 4 vector, which is really the squared magnitude of a 4 vector, and that's just contracting the 4 vector with itself. And in particular, now we refer to this literally as the momentum vector. And the momentum in special relativity, right, is going to always be E over C, first component, second component, third component, which I guess, if I was playing this the right way, I would write is E over C, comma, vector P. When C equals 1, when we use the convention that C equals 1, we would get this expression. If you want to keep your C, right, and you don't set the convention to be C equals 1, then all of a sudden these C squares and C to the 4th start to appear, and you end up with this. So I have in sort of red here the C, arbitrary C convention, and here is the C equals 1 convention in black. Okay, so that takes care of some of the basic 4-vector arithmetic conventions. Now let's look at some of these conventions regarding these derivatives. So the partial derivative, the covariant form, this is shorthand notation for the partial derivative with respect to the muth coordinate, right? This is the muth coordinate, and that's always just going to be straight up partial 0, partial x, partial y, partial z, which probably, because we're dealing with mu, I probably should have written that as partial 0, partial 1, partial 2, partial 3, right? So 1, 2, and 3, x, y, and z. That's really quite different because remember, this is an index, and that index is a number. So if you're going to say partial with x3, there better be a 3 over here. And so that's why I just fixed it with red. But in your head, you should always be able to quickly say x goes to the index 1, y goes to the index 2, and z goes to the index 3. So if you start slipping up between the two, or for some reason you want to clarify without using numbers, or you don't want to deal with, an extra subscript, right, or an extra superscript like x to the 0, say you took that and you raised, you had some weird formula where you wanted to raise some number to the power of the 0th coordinate or something. Now you have a superscripted superscript, right? You have a, the exponent, and the exponent's got a superscript. So you could just write a x or a y or a z. I don't know why you'd ever do that, but I'm just giving you an idea about why you might want to switch from numbers in the convention to letters. All right, so I fixed it. I put letters. I put numbers there. But this is also simplified. The partial 1, partial 2, partial 3 is given by is going to just be given by this gradient operator, which is a vector. Notice I have it as a vector operator. So that's another notational simplification. And because it's a vector operator in order to allow you to do things like dot products after it, right? So you can dot it into some other vector operator. And then likewise, just as we talked about up here with the covariant and contravariant components, the sign switches when you switch from covariant to contravariant. But in this case, you see that the covariant part doesn't have the minus sign in front of its little vector piece, but the contravariant part does, right? And that has to do with the fact that we like to consider this to be naturally in the lowered position and alternatively in the raised position. It's just, again, the convention. And then the other really important convention to understand this work, not the Klein-Gordon equation, but the Dirac equation, not to mention non-relativistic quantum theory involving spin, right, is the Pauli operators. Usually these three here are called the Pauli matrices, 1, 2, and 3. This is the form. Almost every textbook I know uses this form of, well, every textbook I know uses this form of the Pauli matrices. They all use different forms of the so-called gamma matrices, but we're going to defeat that by talking about different gamma representations when the time comes. But they all use the same Pauli matrices, and then we should always add a zero Pauli matrix, a zero 2x2 matrix, which is just the identity. And so these four are the convention that we will use for our Pauli matrices. And there is another convention here, which I didn't write down. I better write it down. Hold on. Okay, so the convention that I should write down is that you can go with an upper space-time index on sigma, right? You have four sigma matrices. They can be fairly organized into with a space-time index, where the first entry is the unit matrix, right? So when you see a 1, it's the unit matrix we're talking about here, right? Not the number 1. And then the 3 Pauli matrices are again formed in this this convenient vector notation. And this is supposed to mean, again, sigma 0, sigma 1, sigma 2, sigma 3, because sigma 0 is the identity matrix. And then if you throw a bar on it, right? Notice I'm throwing a bar on it, but I'm not lowering this index. So the barred version with the contravariant index just suddenly takes that minus sign that you'd expect if it was lowered. So this is a convention that is used just to simplify some work. It's not particularly profound. So just keep it in mind. It's used in Peschkin and Schroeder. And then I guess while I was at it, I am going to do this obvious expression, sort of, need to know expression that the product of any two Pauli matrices is given by this convention here, right? Where I and j can only now run from 1, 2, and 3. So now once we've introduced the possibility of a spacetime index that uses 4 indices, now you distinguish the Greek letters for spacetime indices and the Roman letters as indices for just the spatial part of the 4 vector. So you get this unit matrix here if I and j are the same, and if they're not, you get some sign times I times the third of the 3 Pauli matrix, meaning the product of any two is proportional to the third one. And this epsilon ijk enforces that. I, j, and k must all be different. I assume you know this, right? It's definitely a prerequisite to understand the epsilon notation, certainly the delta notation. And then there's these 2 other forms where sigma plus, this is just this matrix, sigma minus is this matrix, and they're linear combinations of sigma 1 and sigma 2. And yes, there's always a preference here, right? These are a little bit asymmetrical in the sense that sigma 3 is the diagonal Pauli matrix. So it ends up getting treated quite differently. Sigma 1 and sigma 2 that are non-diagonal, you'll see there's value in combining them together sometimes. And sigma 2 actually, like gamma 2, they come in strange places. You think, oh, these 3 are always going to be introduced in exactly equal ways, and they're not. There is a certain amount of favoritism for the diagonal version that makes things seem a little weird. And now the math of all of this, especially with the Dirac equation and with charge conjugation and things, you start seeing weird preferences. There's a preference for gamma 0 and sigma and gamma 2 and sometimes sigma 2, and you just get used to it. Some are preferred in certain situations, not preferred, I guess some sort of stand out in certain situations. And it all can be traced, I think, to the fact that sigma 3 is diagonal and that sigma 2 is purely imaginary. These are all important facts that manifest themselves in various ways when you go through the theory. Okay, so that was a quick introduction to the conventions that we are using. I'll just do this one other convention, right? The quantization. Let's talk about that. And the other conventions are, what are the quantum mechanical operators that we use when discussing quantum mechanics, I guess, is what we're talking about. I call it right now, I'm calling it first quantization. That's a little bit weird. I'm using that, and notice I put it in scare quotes, because nobody ever actually calls this stuff first quantization. The reason I'm calling it first quantization is I want to motivate why sometimes in field theory books you'll see the word second quantization, right? You'll see the idea of second quantization. But the point is this: we all know, because we know quantum mechanics, that there are these axioms of quantum mechanics, and one of the axioms says you take your stuff that you find in classical mechanics, in particular the momentum, the vector of momentum, the notion of energy, the notion of position, and you replace these classical ideas, these classical quantities, you replace them with operators. Right? And this idea is an axiom, right? I keep emphasizing this. Why do I emphasize this a lot? Because it confused the heck out of me when I was a student. I had this idea that you had to be able to go from, look, we studied classical mechanics, we're really good at understanding all these classical mechanical quantities. We're now going to learn the next more advanced phase of physics, and you're going to tell me why we take these classical quantities and replace them with operators. And the reason why you do this is because it works, and because these really smart guys thought about it, and you got some severe philosophical shift when, I guess it was Heisenberg that decided, hey man, let's just say the only things that matter in the world are things you can measure, which is a strangely bizarre thing to say in a time when they really believed that they were on top of the entire world with just classical mechanics. To say that you can't even ask questions about things you can't measure is just weird. And from that point, somehow these guys figured out, hey, what we got to do is take these classical quantities, replace them with operators, decide that all physical states are represented by states in a vector space, and what we're doing is we're solving for these stationary vectors. That's all just invented stuff these guys thought hard about, tried, figured out, and it worked, and it ultimately became an axiom, right? That is the explanation. There is no straightforward way to get from the classical theory to the quantum theory. There's no clear path to doing it. It takes some kind of human super duper insight to get this done, and it took a long time and a lot of really smart people, and this confused the heck out of me. So I constantly am amazed that this, every time I study it, and this is years and years and years of studying this stuff, I'm still just amazed that we're learning this as an axiom. So anyway, the idea is if you take your classical quantities of energy and you replace it with I h bar partial 0, and your classical quantity of the momentum vector, and you replace it with minus I h bar del, right? Which using our convention would be minus I h bar partial I, right? Where I runs from 1 to 3. And, well, that would be, for example, that would be P operator I, right? That's what this would be here. Okay, just to be clear, because again, the notation, this is a vector, this is a vector, so I can't just replace this with an indexed object, because that's just one derivative operator depending on I. If there's an I over here, there needs to be one over here, but there's not, because this has been replaced with this nice convenient vector notation. So I have to rewrite it so that there's an I. And even here I've screwed it up, right? Because I put the I in the contravariant position, and it should be in the covariant position like that, right? Actually, that's exactly what I did right here. So I've rewritten what I immediately knew to be a problem, and I reflected it this way. This is the correct form. So yeah, so this is the momentum operator. Now I put h bar in red because most of our conventions will have h bar being set equal to 1. So you will see this with and without an h bar depending on your textbook. Peschkin and Schroeder uses the c equals h bar equals 1 convention, so you will not see the h bar in a lot of the work we do because we will be parroting and mimicking Peschkin and Schroeder pretty routinely. So here's the point. I guess I need to explain this part. When you take these classical quantities and you replace them with these operators and you create quantum mechanics, you have quantized the classical theory. You've taken a classical theory, made this replacement because of this axiom, you have quantized it. You have caused the act of quantization. That is what it is. Then you start solving those problems, and that's where all of the free particle and the hydrogen atom and the particle in a well and the one-dimensional scattering, all that stuff, the solution of differential equations generated by this quantization prescription, that's quantum mechanics. That's all prerequisite to quantum field theory. But you could say you've quantized the classical theory. And if that's all you knew, you would never say the word first quantization because you don't know anything about the possibility of quantizing it again, right? But what happens now is in field theory is you do this process, so you're staring at quantum mechanics, and the next thing you do is you now start working with variables that are, or you start working with physical quantities that are fields in space-time. And then when you do that, ultimately you end up creating these operators, these things called creation and annihilation operators, or field operators, right? You call them field operators. And this really is in quantum field theory, right? So this is not prerequisite. This is actually quantum field theory. The point is when you create these field operators, you're going to assert commutation relationships between them, right? You're going to assert a commutation relationship between these guys. Again, it's going to be an axiomatic choice, right? But it's different. It's different than this, right? It's an additional level of choice that you make. And that is what we call second quantization, because you've introduced another fact about these operators into the system. And that's second quantization, and that shows up when you study field theory. So in quantum mechanics, you never really say first quantization because all you've done is quantized. You didn't know that there was a potential of doing it again, right? Who would have thought, right? So that's why I'm calling this the standard process, axiomatic and fundamental to quantum mechanics that we discussed in one of our earlier prerequisite lectures when we talked about the axioms of quantum mechanics. That is first quantization. Okay, so where does this leave us? Well, let's see. Before we move on, I should say that it's not necessary to go through this idea of first and second quantization. You can skip first quantization altogether and get into field theory with a single act of quantization, which is, in fact, I think how Peschkin and Schroeder does it, if I remember correctly. But the point is many books don't, and I wanted to give this thing a name. But that is the convention. So now the next step is we're going to start just rolling through these conventions and looking at the classical Klein-Gordon field, what it means, how it's derived. We're going to derive it from a Lagrangian. We're going to derive it straight from relativity. We're going to look at its Hamiltonian form, and we're going to look at its nether currents and structure in spacetime. And that'll be next time. Very important to understand the Klein-Gordon equation because it is sort of the first and simplest of them, and it is very important, pedagogical equation in field theory. Almost every book starts with it, so we're going to cover it as well. Okay, so with that, I will see you next time.